Hello and welcome. My name is Misha Spiegelmach. I'm the founder of the software services company JetBridge, and today we're going to take a look at building an IoT application as lazily as possible using tools and features provided by AWS. So just real briefly about me, I'm a Berkeley, California native, been a software engineer professionally for about 15 years. I'm AWS Solutions Architect. I design and engineer cloud-native applications, and I'm founder at JetBridge. Now, today we're going to take a look at what's involved in putting together an Internet of Things solution using a recent commercial project we worked on as a case study. I want to talk about the overall architecture that we designed on top of AWS, with a special focus on some of the unique challenges in delivering a useful product involving not just pure cloud-based software, but also the embedded components that make up an IoT solution that can be physically deployed to customer sites while still seamlessly integrating with the cloud. So I'm personally a huge fan of serverless, not just the technologies, but the mindset. The concept of delivering maximum business value while building and maintaining as little of my own infrastructure as possible is what I'm all about. AWS provides a wealth of useful pre-built solutions that I can take advantage of, allowing me to focus more on the distinct functionality of my product instead of reinventing some wheels. So IoT stands for Internet of Things, and the serverless aspect of this talk is mostly the I part of IoT. The thing is a server, sort of, but there is some overlap with technologies that are often a part of serverless. Our thing and our backend can both be built on a common platform. In this instance, we'll be talking about AWS Lambda. So the tech stack that we used for this project includes Lambda, along with AWS IoT Core to keep track of our deployed devices, to be referred to for the rest of this talk as things, to use Amazon's terminology. IoT Core provides a thing registry, authentication and authorization of things, storing configuration, lightweight messaging with the MQTT protocol, secure tunneling, and provisioning. In addition, we'll be taking a look at Greengrass, a service for managing running code on our things. Lambda to define the functions that get deployed with Greengrass, and of course, our favorite embedded operating system, Linux. So I'm going to talk about a recent practical project that we had before us to give you a realistic picture of what's involved in a functional system. So we recently built a solution for remotely monitoring some radio equipment. The goal of the project was to collect and report back on the health of some radio hardware deployed at various locations around a city. We wanted to deploy embedded Linux systems to the site to interrogate the radio devices at the site and monitor their health, and then relay their health status back to somewhere central so that we could keep an eye on the systems and ensure everything remained active and functioning properly. Here's what some of the radio hardware looked like. Now, when we were designing software to interact with the hardware, one kind of wacky thing about this project is that I never actually got to see the hardware in person. I had planned to visit the client site to do some hands-on work and debugging, but unfortunately COVID struck this year and travel plans became unfeasible. Buying and configuring this complex and expensive hardware on our own wasn't really an option, so all the work had to be done remotely with remote desktop and SSH tunnels. The fact that we were able to put together a functioning application built around this hardware using AWS, I think is a testament to the power of the tech stack and the fact that even some hardware projects can be done remotely. That said, this probably would have been a good deal easier if we could have been on site. So anyway, just to briefly summarize the goal of our project, we wanted to monitor the radio hardware on site with the venerable simple network monitoring protocol, report the telemetry and faults back to the cloud, and then view the telemetry and faults in a web user interface from anywhere on the internet. That's the goal, but at the end of the day, I just want to be able to configure a Linux device that I can run code on and have it communicate with the cloud. That's the big picture of what we're trying to achieve here. So some of the challenges we were presented with that were not part of, say, your typical cloud-based application were hardware. Well, we have devices that we want to run in the field. They need to have an operating system image that's pre-configured with packages and software that we need. We need to provision the hardware with our Greengrass client so that we can perform deployments and updates of our code while the devices are out in the field. We need to be able to monitor the devices and fix stuff remotely. And it also had a graphical component where we wanted to be able to drive a touch screen with a display of some of the data that the device is reading locally. So for the hardware, this is the thing in AWS parlance. We tried a couple pieces of hardware. One is Raspberry Pi, which probably all familiar with, and one was the ASUS Tinkerboard S. Now on this hardware, what we had to do was install the AWS Greengrass Client and configure an operating system image. We use Debian. You don't have to, but it's a pretty standard operating system. And we need to be able to provision it with configuration to allow it to connect to the cloud. So we used a Raspberry Pi for prototyping. Now, the Raspberry Pi is very well supported. There's a lot of great software and documentation for how to set it up, including with Greengrass. The Greengrass documentation specifically talks about Raspberry Pis, and building a custom operating system image is very straightforward, and it's cheap and easy to get started with one of these. There's a project called PyBuild, which is used to generate the official Raspbian Debian operating system images, easily customizable for adding custom packages and scripts for things like the Greengrass Client. So it's easy to come up with the demo OS image. Now, one downside of a Raspberry Pi for a commercial IoT project is the fact that its operating system image is stored on an SD card. SD cards aren't necessarily all the highest quality things for storage, and they don't necessarily have a lifetime of years and years. And they're also not usually the fastest interface either. What we ended up using is an ASUS Tinkerboard S for the final application. It's a single board computer. Its size and shape and pin layout are identical to the Raspberry Pi, but it has a few additional features. Most notably, it has internal flash storage, which we can load our operating system image onto. This is much more suitable for long-lived IoT applications that need to run for many years with a high degree of reliability. One nice feature about the internal flash storage is that the Tinkerboard can actually be mounted as a USB hard drive, and you can DD the OS image onto it directly over USB rather than writing to an SD card and physically transferring that card from your computer to a Raspberry Pi. Now, the downside of the Tinkerboard is that we couldn't use PyGen, so building a customized operating system was a little bit more involved. Now, when it comes to building a pre-existing image, there are a number of tools you can pick from. If you're using a Raspberry Pi for your project, I really recommend looking at PyGen. Now, Amazon has a new project called Meta AWS, which is a Yocto layer that essentially installs and configures Greengrass for you. This is a very new tool, and to be honest, Yocto is a lot more of a complex system than you may require for your project if all you want to do is build a Debian image with a few custom packages and configuration files. I really recommend taking a look at Armbian if you're building an ARM-based system that's not Raspberry Pi and you're happy with Debian. And there's other tools as well, like Buildroot. All of these tools do for you essentially the same thing. They automate building an operating system image, kernel, define packages to install, configuration files, and a bootloader. For this project, I wanted an automated build that would configure networking, Xorg for a graphical user interface, set up a SSH server, and install system packages like Python and Qt, and of course, AWS Greengrass. So let's talk about configuring the AWS side of things. The place to start is the IoT Core service. IoT Core is the foundation for AWS IoT. It includes a thing registry, which keeps track of your things, and it handles authentication and authorization. You generate a unique certificate for each thing, which it uses to authenticate to AWS Cloud using mutual TLS authentication. And you can associate an IAM policy document with the certificate to give it access to AWS resources. IoT Core also handles MQTT, a lightweight standard messaging protocol typically used in IoT applications. It lets you define a device shadow, which lets you specify a configuration document for each thing, which is synchronized with the cloud and your thing. So even if your thing isn't online all the time, when it comes online, it'll synchronize this document from your thing to the cloud and the cloud to your thing. It can be very useful for storing state and configuration for each device. And IoT Core also provides a secure tunneling system, which is very useful for remote administration. Now, I won't go too in depth about IoT Core, as there's plenty of documentation and videos about it. I want to focus more on Greengrass and the other practical considerations and challenges that you won't maybe find quite as much documentation about. So AWS Greengrass is Amazon's solution for performing more high-level management and tasks on our things. We can define states that we want our devices to be in, including function, system, logging, and secret configurations, and safely deploy new versions of these configurations to devices out in the field. Greengrass encompasses a number of features, but I think the most interesting and relevant for our application is the ability to run Lambdas on your things. With Greengrass, you define a core, which is typically associated one-to-one with a thing. This core includes version and configuration definitions and can also act as a local IoT gateway for other microcontrollers and devices that you may also have deployed on a local network. It supports the MQTT messaging protocol, both for local area networks and also acts as a bridge to the AWS cloud. Greengrass is run as a system daemon process that, among other things, runs Lambda functions locally on your thing's hardware. It's what receives code deployments and allows you to remotely update your things. To set your client up with Greengrass, you need to install the Greengrass Client software along with some configuration. The configuration consists of Amazon's root certificate authority, along with a uniquely generated private key and certificate for each thing. The certificate, along with the thing's ARN and the AWS endpoint address, are used by Greengrass to connect and authenticate to the cloud. The Greengrass Client software is run as a daemon with systemd or your choice of init system. The key, certificate, and Amazon's root CA are fed into the Greengrass configuration file. The policy and thing attachment determine what access the Greengrass client identity has when it connects to the cloud, what MQTT topics can it access, what metrics and logs can it send to CloudWatch, and you can define what other AWS resources you want your thing to be able to access. This is really powerful, giving your thing's identity access to AWS resources. It lets you put some of the responsibility for delivering things like messages or customer alerts to the client devices in true serverless fashion, rather than having your backend coordinate everything. Now, I hope it goes without saying that you need to be careful in drafting your thing's policies, since now anyone physically holding one of your devices inherits all these permissions. So you need to be really thoughtful about exactly how much access your thing has and to what resources. In order to fully provision a thing as a Greengrass client, there are a number of steps to follow. You need to generate a certificate to allow your thing to connect to the cloud and define IAM policies to go with that certificate. We need to create a thing in the thing registry, need to create a Greengrass group version, and then create a Greengrass group. You need to spit out a Greengrass configuration file that gets loaded onto the thing for the Greengrass daemon. And finally, when the Greengrass client is running, then you need to create a deployment of that group version to your Greengrass device. You can perform all of these steps by making a series of AWS API calls, which is what we did. However, since then, Amazon has introduced a feature called fleet provisioning, in which you can define provisioning templates to automate a lot of this process for new devices. I recommend taking a look at fleet provisioning first before trying to do all this by hand. There are a number of ways to install the Greengrass client software on your thing with a tarball, apt-get, Docker, or with a snap package. They all achieve the same thing in the end, which is installing a Greengrass executable in the /Greengrass directory and configuring your init system to start the agent when your system boots up. I find that downloading the tarball, unzipping it, and then adding a systemd service file is pretty straightforward, but do whatever you're into. Be aware that the Debian apt package version won't work for receiving over-the-air updates for Greengrass, though. Okay, so at this stage, we have a Linux device configured with its certificates and running the Greengrass client. What can you do with it? What does having Greengrass running get us? Well, the most important thing is that we can perform deployments to the device now. So what does it mean to do a Greengrass deployment? Deployment consists of a group version definition. This is a versioned group definition which defines what configuration your thing should be in. The configuration can define things like what local devices it talks to, how logs get captured and sent back to CloudWatch, the IoT Core thing ARN and certificate, event subscriptions, and function definitions, among other things. All of these definitions are documented in some detail, and there are a lot of options, so I'll just try to highlight some of the most useful and important pieces for our purposes: the function, subscription, and logger configurations. Once you've created a group version definition with the create group version API call, you can call create deployment to deploy it to a device. In practice, this is how you push out new function code and configurations to your things. Now, I know you've always wanted to run Lambdas on your embedded Linux devices, and now our good friend Greengrass has made that a reality. You can deploy code you want to run on your device as an AWS Lambda function to the cloud, and then deploy that function to your thing using Greengrass. The way you do this is by creating function definitions, which reference your Lambda functions and also offer special Greengrass features and settings. For example, you can specify what Unix user and group to run the function as, run it containerized or not, and since you're providing your own compute here, there are no hard time or memory limits. You can enable an option to always have your Lambda running instead of timing out. This is the console interface to create a new function definition version. If you're managing more than a couple of devices, you'll definitely want to automate this with API calls. Here's a function configured to run forever as root, that is UID 0, in no container. It also has a timeout value set, but it's ignored because the Lambda lifecycle here is set to long-lived instead of on-demand. This means that when your thing boots up and starts the Greengrass client, Greengrass will activate your function automatically and it'll let it run forever or until it exits. So Greengrass has a lot of other goodies that we're not going to talk about. It has the ability to update itself, over-the-air updates. You can deploy machine learning models to your things and run inference locally. It has data stream management where it can send streams of data to Kinesis or IoT Analytics or S3. You can even deploy secrets from Secrets Manager to your thing in case you need to make, say, external API calls. And it has a lot of pre-built connectors that let you drive certain pieces of functionality with MQTT messages, things like controller area networks or Raspberry Pi GPIO pins or lots of other things. Now, let's talk about monitoring. Monitoring IoT devices is a bit more complicated than, say, monitoring a backend service. We need a mechanism to push Lambda and system logs from our thing to the cloud where we can keep an eye on them and be alerted of any errors or crashes. It's important that we have observability into what's going on with our things out in the field. Fortunately, Greengrass solves a lot of this puzzle for us. We can define logging configurations that automatically scoop up logs and output from our Lambdas and the Greengrass system and automatically transmit them to CloudWatch logs. We can even set the log level filter for what we want to capture. As with any CloudWatch log groups, we can create CloudWatch log subscriptions that trigger a Lambda function when new log messages come in on the cloud side. With this setup, you can do anything you want with the logs that your things generate. I like to send the Greengrass system logs to Slack because, well, I'm really lazy and I like to view my logs in there for debugging. If your devices generate any kind of metrics, you can have your devices push those metrics directly to CloudWatch metrics, which I highly recommend. You will need to give your thing permission to do so in its IAM policy. This is a great way to collect telemetry, and you can also set up CloudWatch alarms that will notify you if metrics stop coming in. This way you can be immediately notified if a client goes offline. AWS IoT Core provides a mechanism for securely tunneling traffic to your devices. With an API call, you can open a tunnel, which automatically triggers a message on a special MQTT topic. You can then use an AWS tool called Local Proxy to send and receive data to the device tunneled over WebSocket and MQTT. It's a little bit tricky to set up, but it's well worth it. What I do is create a Greengrass subscription on the special tunnel topic, which triggers a Lambda handler when the tunnel is initiated. This Lambda starts local proxy up on the thing, forwarding port 22 through the tunnel to localhost. I can then start local proxy in source mode on my laptop and then SSH in to the thing. I've used this to debug my code halfway around the world, even tunneling X11. Now, X11 over SSH over WebSocket over MQTT isn't exactly the fastest thing in the world, but it does actually work. Of course, this is an incredibly useful tool for remotely debugging issues. You can find more information and a walkthrough of how to set it up in the IoT Core secure tunnel documentation. One way to run Lambdas on your thing is to set them as long-running tasks. These will be started automatically on boot and run forever. But you can also have Lambdas that are triggered by subscriptions to events. The most basic subscription setup is to have Lambdas that are triggered when a message comes in on a particular MQTT topic. In the example we see here, we can see that when a message is received from the AWS IoT Cloud on the MQTT topic hello/world/counter/trigger, it will invoke the hello world counter Lambda function on your thing. You can use this to remotely trigger code to run on your devices from the cloud. You can also post messages from your thing to the cloud and have it trigger functions in AWS. You can hook up all kinds of utility and debug functions to message triggers for communicating with your things in the field. For example, I've set a trigger to gather telemetry from a site and report it back immediately, so I can gather sample data readings for use in test fixtures. I also set up a trigger that remotely reboots a device and one to initiate the IoT Core secure tunnel application for when I want to SSH into a thing. You can use these subscriptions for product functionality as well. If you say, make a cloud-enabled light switch, you could control it from the cloud by sending MQTT on or off messages that trigger a Lambda on the thing to turn the light on and off, like with GPIO. Now, let's talk a little bit about running graphical applications on your thing. To be honest, I don't know if anyone has ever asked if you can run graphical applications with Lambda. Well, in some sense, you can. What you can do is write some graphical code, say with PyQt, and deploy that code using Greengrass to your things. While I would not recommend trying to launch graphical applications directly from Lambda or Greengrass, you can write a GUI wrapper that is automatically started as part of your X session. This wrapper can locate the latest deployment of your Lambda function, import your GUI application code as a module, and then execute that. A simple but powerful solution that I use to keep graphical application up to date on the device is to create a long-lived Lambda function that simply restarts the display manager. This has the effect of automatically starting a new X session with your latest code every time you perform a deployment. What this all means is that you can have an application running on the display connected to your thing with the ability to update it at any time by simply doing a Greengrass deployment. So this here is some sample code that shows you how to locate the directory where the Lambda code is deployed to. So this directory you see here, /Greengrass GGC deployment Lambda, after a successful deployment, your Lambda code can be found here. There'll be a directory for each Lambda. So you can simply look for the latest version of this because it'll have a suffix that includes the version number. So simply find this and sort it by the version number, and that'll be the path to a directory containing your Lambda code. Once your wrapper has located the Lambda code, you can simply add that path to your system module path and then import the code and run the main function for your GUI code. Who knew that we could use Lambda for running graphical applications? Well, sort of, anyway. So to recap, by putting together a Linux device running Greengrass, we're able to deploy and run our Lambda code on site, giving it appropriate policies to upload metrics as we read them from the radio equipment we're trying to monitor and feed that data back into AWS. The monitoring and remote administration capabilities help us to keep an eye on our things and have access to debug them remotely. We can leverage this setup to do things like run graphical applications, long-running Lambda daemons, and take advantage of other Greengrass goodies like data streams and secrets and local area device networks as well. Another part of our application involves the web UI, where users can view metrics and alarms of different devices. The really cool thing about this setup is that I never had to create any sort of database. All the data presented to the client is pulled from IoT Core and CloudWatch. No RDS or DynamoDB was needed. I was basically able to store all the freeform data about client devices, like, for example, their site name and their location in the thing device shadows themselves. So I basically used IoT Core as my database instead. So not only was our solution here serverless, it was also arguably databaseless as well, at least in the traditional database sense. Obviously, I wasn't able to go into full detail about every piece of the puzzle here, and your requirements will probably differ from mine. But I hope this gives you something of a picture of the different pieces involved in a cloud-native IoT project, and should be a nice starting point should you embark on a similar adventure someday. So thanks so much for watching. I hope I was able to shed some light on this new approach to combining embedded Linux systems with cloud-native design patterns, and hopefully save some headaches for the next person trying to implement a similar architecture by sharing what I learned. Enjoy the rest of the conference. Thanks.